Okay, Math 153 students, in this set of notes, we're going to look at something called the Riemann sum, which is used to approximate, in this set of notes, what's called a definite integral. And definite integrals are defined when we have a function and two given x values, a, which is less than b. Then the definite integral of f of x from a to b is written this way: the integral from a to b of f of x dx, which is so similar to something else we've seen called the indefinite integral. And there's a connection, that's why the same type of notation is used. But notice the difference. What we're doing now has a and b. With indefinite or integrals or antiderivatives, there was no a and b. So this is a different but similarly written concept and process. There will be a connection, but on these particular pages, what we're going to concentrate on, as I said, is using what's called a Riemann sum, really learning what that even means and calculating some of those. And the Riemann sums are approximations to this quantity here. The definite integral, the definition is actually the limit of Riemann sums. The limit as n, which is the number of rectangles used in the sum, which is all getting a little bit ahead of things because you will see soon enough what's meant there by the number of rectangles used in the Riemann sum, and even what a Riemann sum is. That's coming. That's exactly what we're going to talk about in these pages. So once we know what a Riemann sum is, the limit as n, the number of rectangles goes to infinity, is what this definite integral is defined to be. That will make more sense once we do some actual Riemann sums in the next few pages. That's going to be what it's all about. So we're going to move on to doing some Riemann sums now. So here's an example. We'll dive right in and get our hands muddy in the world of Riemann sums. It's really not too bad, these problems. Given a graph, I set up the table down below. Okay, you do these on Newton's, you'll have the graph given to you. You can jot down your own table. I just wanted to have it nice and neat in the notes. And it's not the only way to do it. It's just a way to organize the work, you'll see. So given the graph of the function f of x below, use a left Riemann sum with 4 rectangles to approximate the integral from 3 to 5 of f of x, this function. So, as I said, this doesn't turn out to be too hard, the work, but you need to know what the terms mean. That's a lot of it, actually, and where to start. So the very first thing to look at is the interval, a to b, that you're looking at, which is from here. So the value of a and b are 3 and 5. And let me see here, I'm going to use a blue and mark those here. So we're going from 3 to 5, we say. The integral from 3 to 5 of this function. And then the next thing to look at is how many rectangles is stated for the Riemann sum. 4 rectangles. And then what you do is look at your interval from 3 to 5 in this case and figure out how to break that up into that many equal parts. So it would be like this: 1, 2, 3, 4 parts. Now, very important to doing the Riemann sum is going to be what is the length of each of these equal parts. So that's going to be 1/2 a unit. 1/2, 1/2, 1/2, 1/2. So just to recap and summarize where we're at and what you always do. So you look at your a and your b, and that determines your interval on the x-axis you're looking at. And then you look for your number of rectangles and divide that interval up into that many equal parts. and figure out what is the length of each of those sub-intervals within the interval from 3 to 5. Once you divide that up into 4 equal parts, each of those intervals marked by the green marks is 1/2 on the x-axis. So that's that. So far, so good. First this, then this. Now, there's always going to be a word left or right, and that's the next thing to look at. This is the word left. What that's referring to is a left-hand Riemann sum we'll use for each of these subintervals down here. We have to use either the left or the right-hand point on the x-axis. In this case, it's a left-hand Riemann sum. So for this, the first interval, we would use this point. So I'm going to draw a line up to the point on the graph of the function and create a rectangle over top of the first of our 4 subdivisions based on this left-hand point. Now, for the next interval, which is right here, the left-hand point is here. So I'm going to use that to create the second rectangle, which would be like that. For this, the third of the 4 intervals on the x-axis, so I'm looking here at this interval, I go to the left right here. I'm going to create a rectangle using this point on the graph. So the meaning of the word left is as I create these 4 rectangles, I'm using the left-hand endpoint of the green intervals. So in the last case here, I'm going to use this point. I'm going to go up to the graph of the function, whatever point that shall be, and draw a rectangle like that. Okay? Now what the Riemann sum is going to turn out to be is the sum of the areas of those 4 rectangles. So to get those areas, what I want to mark here are the heights of these rectangles based on the y values. So the height here will be 5. The height of this rectangle will be 3. The height of this rectangle will be 2. And the height of this rectangle would be 4. And it's based on the y values of the points that we're using. We're using those points because it's a left-hand sum. So the left-hand sum part means whatever our intervals are on the x-axis, we use left-hand point, create a rectangle, left-hand point for the next one, create a rectangle, and so on, just as I did there. So kind of don't overthink that part of it. That part right there can be the trickiest part of the left and the right part. The left is referring to look at the x-axis, go to the left. Next interval, go to the left. Next interval, go to the left. Alrighty, now, what about this table right here, this chart? The chart's kind of the easy part. If you see how those rectangles are built, so to speak, we fill in the blanks now. For rectangle 1, the width is 1/2. Talking about R1 right here, and then I'll just go R2, second one, R3, and R4. But for rectangle 1, the width is 1/2, and the height is 5. So, you can see why we want to call height here as 5, but more in rectangle formula terms, that's length times width, or width times length. It's going to be the rectangle area. So 1/2 times 5 equals 5/2. The second rectangle, R2, has also a width of 1/2. And they all do. All 4 of them have widths of 1/2. That's why it was important to figure out what was the length of those subdivisions when we created them. And they were each 1/2 a unit long because we divided up into 4 equal parts. They do have different heights. The second rectangle has height 3, the third rectangle has height 2, and the fourth rectangle has height 4. And so I'm going to multiply width, which is 1/2 in all cases, times length or height. So equals. It would be 3/2. will be 1, this will be 2. So you can take a calculator, just add like 5 halves plus 3 halves would be 8 halves, which would be 4. Plus 1 is 5, plus 2 is 7. So in the cell, I'm talking spreadsheet terminology there, and I use that word cell above, put the sum of the areas of those 4 rectangles. That's the Riemann sum. So that type of sum is what this whole packet is about, computing. And that's approximately what the value of this integral from 3 to 5 of f of x dx of this function would be. The more rectangles that we use in this construction, the better the approximation would be.